Welcome to an overview of the approach we will take to solve nonlinear systems of ordinary differential equations. Except for a few brief detours in Chapter 1, we considered mostly linear differential equations. Linear equations suffice in many applications, but in reality most phenomena require nonlinear equations. Nonlinear equations, however, are notoriously more difficult to understand than linear ones, and many strange new phenomena appear when we allow our equations to be nonlinear. Not to worry, we did not waste all this time studying linear differential equations. Nonlinear equations can often be approximated by linear ones if we only need a solution locally, for example, only for a short period of time, or only for certain parameters. Understanding linear equations can also give us qualitative understanding about a more general nonlinear problem. The idea is similar to what we did in Calculus 1 in trying to approximate a function by a line with the right slope. Recall we used either a secant line or a tangent line near a particular point to approximate a function in Calc 1. So the big idea here is that we'll often use a related system of linear differential equations to get information about the solution to a given nonlinear system of differential equations. For example, back in section 2.4, we looked at the pendulum of length L pictured here on the right. The goal was to solve for the angle theta as a function of time t. The equation for the setup is a nonlinear equation theta double prime plus g divided by L times sine theta equals 0. Instead of solving this equation, though, we solve the easier linear equation theta double prime plus g divided by L times theta equals 0. Notice to form the linear equation, we replaced sine theta with theta. While the solution to the linear equation is not exactly what we were looking for, it is rather close to the original as long as the angle theta is small and the time period involved is short. We can see this by looking at the graph on the left. The graph on the left includes the graph of the function theta as well as sine theta. Notice near 0, the function theta is a good approximation for the function sine theta. You might ask, why don't we just solve the nonlinear problem? Well, it might be very difficult, impractical, or impossible to solve analytically, depending on the equation in question. We may not even be interested in the actual solution. We might only be interested in some qualitative idea of what the solution is doing. For example, what happens as time goes to infinity. In the next lesson, we'll begin our study of nonlinear systems of differential equations by discussing autonomous systems and phase plane analysis.